Oh, good morning and welcome to our June Tech Talk. My name's Wayne Welk and automation specialist with the Reynolds Company in New Orleans. And I'm just going to quickly introduce our guest speaker and turn over the presentation to our guest. Our guest today is Southwire, and Mr. Steve Wetzel, principal engineer with Southwire, is going to present on VFD cables, essential or overkill. I think we know the answer to that question already, Steve, but we'll let you take it from here.
Okay, thank you very much, Wayne. Welcome, everybody. Thank you for joining us. Before we get into this topic, because there's a lot of misconception about what VFD cables can and cannot do, or do and don't do. Just a little bit of background on me. I am an electrical engineer with Southwire. I got my engineering degree from the University of Wisconsin in Madison, which is pretty close to where I am located. My first job in this industry was with Siemens Energy and Automation. And Siemens Energy and Automation actually created the first VFD cable construction, probably because they were the only company out there that had owned at that time a cable company and a drive company. So they understood the need for this and the reasons for this type of cable. It wasn't really sold here in the US. It was mostly sold in Europe. It was a German VDE construction. It had no UL listing. But the concepts, I learned the concepts back then, and that's been with me throughout my career, especially the last 8 years with Southwire, where we have really focused on factory automation. But instead of just trying to push a product, we're trying to push a solution. So there's a lot more to VFD cable than just buy the cable and you'll be happy. And let's take a look at some details. And before we begin, I'd like to set the stage with 3 quick stories. And the first story is when things go well. You've got a customer, he buys a drive, he buys a motor, he hooks it up with THEHN, it's running over in a corner someplace, and it works, and he has no issues. And this happens, and it happens a lot, or the drive manufacturers probably wouldn't be in business. So very common, things just go well. But sometimes things don't go so well. There was a pulp and paper mill years ago that took a line and put in VFDs in their paper making process, and they started having all kinds of problems. They had drive trips, they had motor failures, they had drive failures, they had control issues, communication issues. They tried about everything they could think of: filters, reactors, cotton mode chokes. Nothing was really fixing the problem until finally their manufacturer, the drive manufacturer, said, why don't you pull out that cable and install a VFD construction cable? And their problems went away. So here we have both extremes. But the real interesting one to me is when things might go well, but then again, they might not. There was a steel mill in Indiana, and they were putting a new drive line in. And they went out to all the major drive manufacturers to get quotes for that system. And one of those manufacturers differentiate themselves from the others by saying, well, if you buy our system, you don't need to put drive cable in. Well, VFD cable is more expensive than standard cable, so there was a cost savings associated with that. I'm not sure how much that played a role in their decision, but for whatever reason, they ended up awarding the business to that drive manufacturer, only to have that manufacturer come back at the 11th hour and say, you know, we've been thinking about it, and you probably really should be putting drive cable in. So if the manufacturers don't know for sure, how can we as suppliers and users know for sure what to do in that situation? A drive engineer, it was actually a Rockwell engineer at an automation event in the Dakotas, came up to our booth. I was working there, and he asked me, I said, do you make a VFD cable with PVC insulation? He said he wasn't a fan of that construction. It just caused him problems. And he wondered, why would anybody make such a cable? Well, that is really a good question. Why would anybody make a VFD cable with PVC insulation? So I looked in the NEC. There's nothing in there about it. I looked in the UL standards. There's nothing there. There's nothing in the ICEA standards or IEEE standards or NEMA. I couldn't find any information anywhere. So where does one go when they've looked everywhere for the answer and they can't find it? Well, the internet's one option, but I went to the Bible and I went to the book of Judges. And in Judges 21:25, it says, in those days, there was no king in Israel. Everyone did what was right in his own eyes. Now, this was written thousands of years ago, before we had drives, before we had electricity. And so we need to modernize this and translate it so that it has some meaning today. So I've gone ahead and done this so that we've got actually a truthful nugget here for the factory floor. And what I came up with was this. In those days, there was no VFD cable standard in America. Every manufacturer made what was right in his own eyes. And this is my one and only verse that I've translated, but it's true. There's a lot of confusion in the industry because there is no VFD cable standard in America. Anybody can make anything they want and call it a VFD cable, including constructions with PVC insulation. And we'll see why that's an issue in a little bit. There is literally no such thing as a, quote, VFD rated cable. Yet we get asked to supply one all the time. Well, we're working to fix this situation. I chair a working group on the ICEA, Insulated Cable Engineers Association, that is working to create a VFD cable standard to help end the confusion. The goals that we have for this are to allow only specific constructions to be called VFD cable. PVC insulation won't be one of those constructions, so that'll be in there. We want to standardize some testing and performance requirements. The standard has just gone out for ballot. I expect it, based on the last ballot, to come back and be ratified. So we should have a standard soon. In addition, we're in discussions with UL. They want to create a VFD cable standard. Eventually, we want to get things in NEMA and the NEC so that this cable, this construction, and proper components of this construction are all documented and well understood. So why is this an issue? Why are we talking about cable? And the main reason is because the wrong cable can cause a variety of problems. Literally everything on this list, to a greater or lesser extent, can be influenced by the cable that you run from your drive to your motor. And what's interesting is this is not a logical link for many people. Who would think that a motor failure would be based on the cable running between the drive and the motor? Well, at least the motor's hooked up to it. I guess that makes some sense. But PLCs, they're not even hooked up to this cable. You got a drive on one end and a motor on the other. The PLC's on a completely different circuit. So how in the world could that happen? Or radio problems? It's not a clear link, and we'll see why that is for some of these issues. But they all relate to the same thing, right? It's all decreased productivity, and it's something we want to stay away from. Well, what's the cause of these issues? And I reluctantly have to say it's this thing right here. It is this VFD. Now, the good news or bad news, I guess, depending on your perspective, it's not just Rockwell PowerFlex drives. It's also ABB drives and Eaton drives and Siemens drives and basically every low voltage drive out there. And the cause really doesn't have anything to do with this that goes into this drive. It has to do with this nasty pulse width modulated waveform that comes out of the drive. Now, IEEE papers tell us that this waveform, this series of different width square waves, has frequency up to and over 30 megahertz. So we're basically dealing with frequencies about 1 million times higher than what we have coming out of the wall. And that causes some issues. Well, why is this high frequency a problem? Let's do a little cable engineering 101 to give you an idea of what we're dealing with. The main reason high frequency is a problem is because things change. Now, I've got my little circuit diagram up here, and I am modeling the cable conductor with an inductor L sub C and a conductor resistance, right, R sub C. And I'm modeling the insulation with a capacitor and a resistor in parallel going to ground. The C of I and R of I are my insulation modeling. Now, I'm not going to look at all four of these components, but basically, to be real simple, we want the resistance of the conductor to be low so we can push current down it without creating a lot of resistance or voltage. And we want X sub C, which is the resistive component of the cable insulation, the resistive component of the capacitance of that insulation, to be high, so we're not leaking a lot of current to ground. Now, if we take this cable, just a single conductor 5 kV cable, to simplify things, we run those numbers at 60 hertz, we get exactly what we want. We have a very, very low AC resistance. We have a very high capacitive reactance. And we're also going to look at EMI, which is proportional to the current times the area of the loop times the frequency squared. And we don't know enough about that to have all those numbers. So I'm just going to use the unity value there for comparison. But now if I do those calcs at 10 megahertz, everything changes. My AC resistance goes up by 178 times. My capacitive reactance goes down by 163,000 times. And my EMI literally increases by 1 trillion. Everything changes. Everything changes in the wrong direction, and it all changes in a big way. This is not good. And this gives you a hint as to the issues that we can have with VFD systems. Now, before we go any further, what is a VFD cable? Well, today it's hard to say because there's no standard, but we can look at all the constructions out there, the IEEE papers, and determine what the optimal cable construction is. The optimal VFD cable construction consists of 3 things: an overall shield, a robust insulation, which I'll define further later, and a symmetrical or 3+3 design. Now, if we look at all the cables that are out there, we see that basically 100% of them have an overall shield. I'm not aware of any cable out there that's called a VFD cable that doesn't have an overall shield, but not all of them have a robust insulation. And even fewer have a symmetrical design. Well, why is this? Because there's no standard. So anybody can make anything they want and call it a VFD cable. Well, let's take a look at each of these 3 components and see why they're so important. And we're going to start with the overall shield. And we're going to start with a simple diagram and simple concept. And we'll move up, we'll build on this to some more complex concepts as we go on. But we're first going to look at the overall shield's performance in terms of electromagnetic interference. Now, here we have a drive, a motor, and an unshielded power cable. And in this situation, because of those high frequencies that are put out, this power cable acts as an antenna, and it broadcasts interference throughout your facility. Now, that interference is proportional to the current times the area of the loop times the frequency squared. So what happens if possibly maybe we've got an alarm that sits close to that cable? Well, that alarm can trip and go off. And actually, I was talking to a customer just a short time ago about just this situation. They had a bunch of drives, they had a bunch of motors, they had unshielded cable in their facility, and they introduced a new alarm into their manufacturing process, and they installed some CO2 sensors. Well, these sensors were going off all the time. This must have been a very dangerous place to work. But there was no problem with CO2. It was all EMI that was setting these alarms off. And after quite a bit of troubleshooting, they determined that if they could install these alarms in an area where they had shielded cable between their VFDs and motors, they were not having issues. It's not a cheap problem to solve because replacing cable's typically very expensive. So if we put a shielded cable in, though, that shielded cable, provided it's grounded on one end, we can drain that EMI off. We get a lot less emissions in the plant, and everything can work fine. Now, the next issue relates to safety. And you can see we've doubled the complexity of our diagram here. Now we have 2 drives, 2 motors, and 2 unshielded cables. And we're going to say that these cables are run together for a fair distance in some cable tray. And we need to do maintenance. So what do? Well, we lock out and we tag out, and we bring our little electrician in to do, or a big electrician for that matter, doesn't really matter, but he goes on, does some work on that cable. And what can happen is through electromagnetic coupling, we can get a potentially dangerous or potentially fatal current and voltage flowing in that locked out system. And you don't have to believe me on that. That is in this IEEE paper, Evaluation of Power Cables for Pulse Width Modulated Systems. And basically the bottom part says if two motor circuits travel a considerable distance together, in tray, for example, the open circuit may receive enough electromagnetic electrostatic coupling from the energized circuits to produce a driving voltage and current flow that could be dangerous or potentially fatal. So we definitely have a safety issue here. Fortunately, we can remedy it by using shielded cable, because again, by using shielded cable, not only reduce that EMI, we reduce that coupling. So when we bring our electrician in to do some work, we don't have that significant voltage and current induced in that locked out system, and he can work all day, go home at night and watch Netflix or do whatever else he does at the end of the evening. Another issue that the overall shield deals with is common mode current. Common mode current is defined as the sum of all currents flowing in a cable. So if we add up the three phase currents, if we add up the ground currents and the shield currents, add all those together, we want to get zero or close to zero, or there can be problems. Now, with a traditional system, traditional power, we don't have a problem, right? With three sine waves equal amplitude, 120 degrees out of phase, they add up to be zero. It's a wonderful thing. Typically, we don't have any ground currents. We don't even have shields on most medium voltage, on most low voltage cables. So I think it was my sophomore year at Wisconsin, I learned that 0 plus 0 plus 0 equals 0. So with traditional power, we're usually sitting pretty good. But in a VFD system, we have issues because those phase currents do not sum to be zero. This lovely equation does not apply. The phase currents look something like this, which just really super noisy waveforms. We'll talk about ground currents and shield currents later, but what does the sum of these phase currents look like? Well, it turns out it's a lot of current. In fact, I had one drive manufacturer tell me that they had measured in their lab over 100 amps of common mode current flowing. Now, it's not high power. You don't need to derate your cable for this. It's noise, but it's a significant amount of noise. These peaks can be very great, and that can be a shock hazard, or it can cause interference with nearby electronic equipment. Tens of amps is not uncommon to be measured in a situation like this. Well, why is this a problem? Well, we'll look at another diagram, and you can see I've once again modified my diagram. I've now added in a I-beam and a ground grid to this drive system. And what happens is that common mode current, that net current flow, gets pushed down the cable to the motor. Now, per Kirchhoff's law, that current has to return back to the drive. But how's it going to get there? Well, it's high frequency current. So it likes to flow through large surface areas like building steel due to the skin effect. So this current can flow through the motor frame and base plate, through building steel, and then eventually somehow find its way back to the drive. We don't know the path it's going to take. It's going to take the path, it's going to take all paths, but it's going to primarily flow through the path of least resistance. Now, we know 100 amps has been measured in some cases of common mode current. And if that's sitting on the ground someplace, what's going to happen to this PLC if it's connected right up near where that significant high frequency noise current is flowing? Well, it's probably not going to spontaneously combust, but it is going to have issues. It may die. It may just have intermittent operation. If it's an alarm, it might trip. It can get definitely confused. Maybe needs to be rebooted. Who knows? But it can cause issues. Now, again, I said we don't know where that current's going to flow. It may go all the way back to the input transformer and then back to the drive. And so anything along its path, it's possible you could have issues with. And it's not apparent upon first look that there's any reason you should have an issue with that system simply based on the cable running between your drive and motor. We'll look at that a little bit later on. Now, in addition, we typically hook things up to our motors, right? So if I've got some machinery that's running off the motor, I now have another path. That current can flow through the motor bearings, through the factory machine, and then eventually back to the drive. And if that happens, we can have motor problems. Now, motor failure can be caused by current flowing through the bearings, which causes bearing flutings, and it creates these repetitive ridges in the bearing race like you see. Then this fluting causes noise, vibration, and eventually failure. Unfortunately, that failure doesn't occur for 3 to 12 months after the system startup typically. So you could have a new drive system, think everything's going along just fine, and 6 months later, you start burning through motors. What's going on? You don't know. This could be the issue. Now, some people think an inverter duty motor is the solution to this, but it's not. Inverter duty motors were created to handle reflected waves that were shorting out the windings of the motor's insulation before the IGBT drives were introduced in the 90s. And that insulation, that increased insulation, does protect the motors from that reflected wave, but it does nothing to protect the motors from bearing fluting at all. Now, you could use a shaft grounding ring or brush or ceramic bearings, but to me, those are not optimal solutions. They will keep the current from flowing through the bearings, but they don't solve the overall problem of that uncontrolled common mode current. It's still going to be flowing in your system, and maybe instead of going through the bearings to factory machine, it just goes through the motor base plate and then somehow through building steel and infrastructure and eventually back, but that can cause issues with other systems as well. So we also should look at this from an electromagnetic interference point of view, because we have more information now, right? We know the formula. EMI is proportional to the current times the area of the loop times the frequency squared. And we know the current can be significant, right? 100 amps has been measured, and we know the area of the loop can be very large. If you look at any of these loops, that can be significant. So all that can relate to significant EMI in your system. Well, what can we do? We can use a properly terminated VFD cable. What we want to do is create a low impedance and high frequency controlled path for that common mode current. Rockwell suggests we do that by using large surface area terminations of that shield at both ends of the cable. Now, some people, this is news to many people actually, because a lot of electricians were taught for low voltage cables, you terminate one end of the shield at the source. So some of your electricians are going to want to float it at the motor and terminate that shield at the source. Now, if you do that, you still get the radiated EMI protection, but you don't provide that controlled path for the common mode current to flow back to the motor. We want to push that current onto that large surface area shield. And in order to have that shield carry it back to the drive, we have to terminate both ends of that shield with a low impedance at high frequency termination. So low impedance, high frequency indicates that we use large surface areas. So don't use pigtails or small drain wires. Use VFD termination kits or VFD cable glands. Rockwell calls this a 360-degree termination. And we can help with this. We have products to help you. We have VFD cable glands where you can use this gland and it wraps all the way around that shield and provides an electrical connection between that shield and the enclosure. We have VFD termination kits, which consist of a copper braid shield, a constant force spring, and some copper foil tape that you can wrap around the shield and terminate that way. We even have training videos on how to use them. We also have application notes to help you understand and help communicate these concepts to management that may need to be involved in the decision. So now that we have a properly terminated VFD cable, we control the path of that common mode current. Again, as we saw before, it gets pushed down the cable to the motor, but now we're going to send the bulk of it back through the cable shield, and we're going to minimize the currents flowing everywhere else. And that's going to give us a much better chance of successfully operating and not having electromagnetic interference that's going to mess with other parts of our system. Oh, conduit alert. Almost forgot. Conduit is not a solution. Some people think, well, I can just take some THHN, throw it in conduit, and I've got a poor man's VFD cable. But conduit is typically installed as a mechanical solution, not electrical, and it's not maintained as such. It also doesn't provide a safe path for that common mode current because it's not insulated. And wherever that conduit comes in contact with building steel, which happens a lot, that's a potential jumping off point for that current so that it can become uncontrolled again. It also doesn't allow for the symmetrical lay of the conductors or grounds, which happens to be our next point. So let's move on to that one. Now, symmetrically designed cables, and they're called symmetrical, what they really are is three-phase conductors with three grounds inside the cable. And those cables are designed, that design reduces ground current flow over a standard four-conductor cable. And it accomplishes this by using some really neat cancellation effects on those grounds. Remember my favorite formula right here? Well, let's see how that applies. So what I've got here with a four-conductor cable is my two phases, my yellow and my brown phase are going to induce a current in that ground wire, and that current will be equal amplitude and 120 degrees out of phase. Now, the orange conductor will also induce a current, and it will also be 120 degrees out of phase, but it will be lower in amplitude. Why lower in amplitude? Because it's further away, it has less of an effect. So when I add this up, I get a non-zero current flowing on my ground wire. Now, with three conductor cables and three grounds, it's kind of messy. It's hard to visualize initially, but if we break this down, it becomes very simple to understand. So let's take these three phase conductors and see what kind of current they induce on our ground conductor. But I'm not going to look at everything all at once. I'm just going to look to the conductor that is clockwise. So the ground conductor that is clockwise from the phase conductor, that's here, here, and here. And that's going to induce currents that are 120 degrees out of phase and equal amplitude. Well, we know from our beautiful sine wave equation that gives us zero, no ground current. And if I look counterclockwise, my second component of three, well, it's basically just the same thing. That gives us also three sine waves, 120 degrees out of phase, equal amplitude. That gives us zero. And if I look opposite, my last component, they're still 120 degrees out of phase, but they're all lower in amplitude, but they're still equal. So it comes out to be zero. So once again, 0 plus 0 plus 0 equals 0. And I put the exclamation point at the end of that. You can interpret that one of two ways. It either means that it's a factorial symbol, which is mathematically correct, or just that I'm really happy that this works out this way. So symmetrically designed cables reduce our common mode current flow, and they also reduce your cable bend radius because the three conductor cable is about 11% smaller than a four conductor cable. In summary, we can reduce common mode current effects by one, controlling its path with shielded cable, and secondly, by minimizing its generation by using symmetrical or 3+3 designed VFD cables. Now, there's another issue that relates to symmetry in some ways, and it's electromagnetic coupling. And this is a story I was told by a Rockwell engineer. And he had a customer that was using non-shielded cables. He had multiple drives and motors, and he had one tray, and he just threw all the cables in that tray in a random way. All single conductors, just toss them in there however. And I've got the circuits numbered here, 1 through 5, right? And what was happening was his drives were tripping. Now, I know they don't trip like that, but I had to have some kind of graphic up there. But anyway, what's the cause of this? Well, the cause is the title, electromagnetic coupling, because what happens is this number 3 brown conductor couples with the conductors nearby it and induces a current and voltage on those. But it doesn't just happen with this to the adjacent conductors. It happens to conductors that are farther out too, but just to a lesser extent because they're further away, kind of like that induced current on the grounds. It's not going to interfere as much. But it doesn't just happen here. It happens over here, and it happens over here, and it happens all throughout here. All these conductors are coupling with the other conductors and inducing currents and voltages on them that they're not used to seeing. And what happens is drives are intelligent devices. And so the drive is monitoring the currents and voltages, and it's saying, I don't expect to see this. I don't know why I'm seeing all these currents and voltages that I don't expect. I'm just going to go to sleep and hope things are better when I wake up. And so then the drive trips out and you've got a problem. Well, what's the fix? Well, my application engineer friend told the customer to go back and group all of these cables by circuit. So that's gonna take some time, and then you need to secure them with cable ties every so many feet. So there's a fair amount of labor involved in that, and we agreed it was a good thing that the customer saved money on buying single conductor cable over drive cable, because then he had the extra money left to do this. But I think there's a better solution. I think the better solution is to install VFD cable. VFD cable has this unique feature called auto grouping of your conductors. You can't get it wrong. Unlike using single conductors, there's no way you're going to get it wrong. And simply by grouping these conductors together, even without the shield, you reduce some of those effects. Now, the shield helps further, and with the VFD cable you get the shield as well, but it's a much cleaner solution to the problem that can be had if one decides to go the route of single conductors. Well, finally, let's talk about insulation. And before we talk about insulation, we need to talk about the voltage that the system is going to produce. And I talked about it a little bit before, reflected waves, or standing waves as they're called, and they are an issue with drives. What happens is, because there's an impedance mismatch between the motor surge impedance, which is high, and the cable surge impedance, which is low, when this waveform goes down and hits that impedance mismatch, it's like a wall, like a tennis ball hitting a wall, and it bounces back. Now, in theory, the voltage doubles, but in practice, it can be even higher. I think it was Yogi Berra who said, in theory and practice are the same, but in practice, they're not. And that's the situation we have here. And as I mentioned before, this is what was causing motor winding failures to be a big issue in the 90s, because motors were not used to seeing this doubling of the voltage on their windings. Well, what's the actual voltage? IEEE papers tell us it's 2 to 2.4 times the DC link voltage of the drive. Now, what that is 1,560 volts on a 480 volt drive system and 1945 volts peak on a 575 volt drive systems. Now, not only are you seeing higher voltages because of these reflected waves, but the peaks, these high peaks are hit at the carrier frequency rate. So, with the 60 hertz power source, you're only hitting those peaks every 1/120th of a second. Here, we're hitting those peaks anywhere from 3 to 12 kilohertz with smaller drives. Now, standing waves are a function of many things, but they're basically a function of power transistor rise time and the cable length. And if you look at my graph here, I've got over voltage on the vertical axis, and I'm just going to max out at the theoretical doubling, 2.0. And then I've got cable length on the horizontal axis. And with old drive technology, gate turn-off thyristors, they had very slow rise times of that. And we're talking rise times, I'm talking about the 10 to 90%, the time it takes to get from 10% to 90% of that waveform of those square waves, those pulse width module waves would come out. So GTOs had very slow rise times, 4 microseconds. So if we did the math, we didn't start to see reflections until 320 feet, and we didn't max out until over 3,000 feet. But what happened is drives got faster. These power transistors got faster. And as we developed faster technology, that pushes this curve all the way down to the left, so that with today's IGBTs, we have a completely different story. We start to see reflections in as little as 4 feet, and we can max out that full reflection in 35 feet of cable. Fortunately, the solution to this is very obvious, right? All we need to do is build really, really small factories. My sales guys don't like it, but if you can keep your cable length, they don't like it when I say this, but if you can keep your cable length to 2 or 3 feet, you'll never have a problem. But you probably can't do that. So in that case, we just need to use cables that can handle those standing wave voltages. So let's do a little bit of comparison on that. On a 40 volt system with and 600 volt cable with both traditional 60 hertz power and a drive system. Well, RMS on a 60 hertz system is super easy. A 40 volt system operates at 480 volts RMS. That's implied. A 600 volt cable is rated at 600 volts RMS. So my cable voltage rating is higher than the voltage that the system is putting out. That's a good thing. If I look over here, RMS, it's pretty hard because I have to take the root mean square of this pulse width modulated waveform, which is not really easy. So we're just going to skip it and we're going to look at things another way, which is actually a better way to look at it anyway. So we'll look at peak voltage. Now, to get peak voltage of a sine wave, I just multiply by the square root of 2. So my 480 volt system puts out 679 volts peak. If I take that 600 volt rated cable, well, that's rated for an equivalent of an 850 volt peak sine wave. And once again, right, I never hit that 850 because my system is putting out 679 volts peak. So I'm good to go. Over here, it's even simpler because that IEEE paper told us on a 40 volt drive system, we put out peak voltages of 1560 volts. But my cable is still rated for 850 volts peak. So I'm hitting my cable with about double the voltage that it was designed to handle. Not a good situation. So the $64,000 question is, can you use a 600 volt rated cable on a 40 volt VFD? And just like everything else in life, it depends who you ask. If you ask the National Electric Code, yep, you can do that, no problem. They don't really have a lot to say about it. But if you go back and look at the National Fire Protection Agency's Standard 79, 2018 version, which is the machine builder standard, they put some restrictions on that. Let's take a look at what that document says. NFPA 79, 2018. I'll just read the paragraph. Electrical conductors and equipment supplied by power conversion equipment as part of adjustable speed drive systems and servo drive systems shall be listed flexible motor supply of cable marked RH. I'm just going to say RH or XH because any of those work, or selected based on equipment manufacturer's instructions. Well, what don't they include here? THHN. Why are they not including THHN? Well, some people say, well, maybe that's because THHN is rated 600 volts. But there's more to it than that. If I look at all these cable types, many of them all of them actually can have a 600 volt rating. Some you can have a higher rating on, but you can get those cables in a 600 volt rating. So it's not just the 600 volt rating. Why not THHN? And the reason is there are a lot of reasons. EMI and coupling, we saw THHN is typically single conductor, and we saw the problem with throwing a bunch of single conductors in tray together for multiple drives. But there's other reasons too. The insulation compound, something called corona inception voltage, wet withstand voltage, cold flow capacitance. We'll take a brief look at each one of these. And we'll start off with the insulation compounds, because if we look at this table, I put the THHN in along with the cables that are recommended by this standard. THHN is the only insulation compound that is thermoplastic. THHN is basically a PVC insulation, which is thermoplastic. All the others are thermoset insulations. Well, what's the difference? And we're throwing a lot of letters up here and a lot of terms. So just to make sure you all understand, my cable type is defined by the NEC. That could be THHN, RHH, XHH, and so on. The insulation compound is the actual material used to make that cable type. For instance, THHN uses a PVC insulation compound. RHH uses ethylene propylene rubber, EPR, or cross-linked polyethylene. So these terms are somewhat used interchangeably, but they do have slightly different meanings. I just want to make sure you're not confused about that. But we have two other words down here, thermoset and thermoplastic. What is that all about? Well, thermoplastic compounds can soften, flow, or distort when subjected to heat or pressure, and they can be remelted when exposed to heat. So if you take THHN and you put a torch to it, you can literally melt the insulation right off that cable. Thermoset compounds Well, they will not soften, flow, or distort when subject to heat or pressure. You can't remelt them when exposed to heat. They'll char, but they won't melt. I like to think of thermoplastic insulations as like popsicles. You're in Texas, it's probably pretty warm down there. So if you stop on your way home at the grocery store and get some popsicles and then stop at a store to pick something else up and you're in there for 20 minutes, when you come back out, you probably don't have popsicles anymore. You probably just have sugar water. And that's akin to a thermoset insulation. Thermoset compounds are more like cookies, right? If you had gotten cookies instead of popsicles and you did the same thing, now you'd only have warm cookies, which in my book is better. You just upgraded them, but they don't ever go back to dough, right? A chemical change has taken place inside those cookies and you can't get them back to their original material. And it's kind of the same between these insulation compounds. Thermoset compounds are more robust both electrically and mechanically than thermoplastic compounds. Now, another thing to look at is 600 volt insulation thicknesses, because different cable types have different insulation thicknesses. And THHN, you can see the insulation thicknesses here ranging from 15 mils to 30 mils for cables from 14 gauge to 6 gauge. And that may seem like a lot or a little to you, but regardless, if I look at the same 600 volt rated cable only in XHHW, I get a significantly thicker insulation, double at the smaller sizes. More insulation is obviously going to give you better results. It's going to handle higher voltages easier. So 600 volt XHHW has 50 to 100% greater insulation thickness than THHN in the smaller sizes. And the next step is corona inception voltage. And this is defined at the voltage at which corona discharge damage can start to occur. Now, when you get corona inside the cable insulation, it causes heat, it causes ozone, and a thermoplastic insulation, it can cause melting. It can be the end of the cable. It can be the beginning of the destruction of that cable. So now voltages below that corona inception voltage don't cause that discharge, that damaging, but voltages above it do. Now, in a 600 volt THHN cable represented by this black line, the corona inception voltage can be lower than the reflected wave voltage. So every time, those red areas of that waveform, every time I cross that black line, I'm slowly damaging that insulation. In 600 volt XHHW, it just has a much higher corona inception voltage. So you never get a waveform that's high enough to do that damage to the insulation. Voltage withstand is another issue. It varies by compounds, but basically XHHW has a higher voltage withstand before it's going to break down. But if you look at wet conditions, humid or wet conditions, thermoset PVC, THHN, 55% lower voltage withstand. So if you've got a humid environment or you're running cable and conduit that can be in water, this becomes even a bigger issue with THHN cables. And finally, cold flow. I think that's my second to last one, actually. So what can happen is with THHN insulation, if it's pulled around a bend in conduit, you can thin the wall, which is not a problem for crosslink. So if I'm pulling this cable in, and I got a 15 mil wall, I may be down to an 8 mil wall, and then that can cause other problems, right? So THHN has been shown to fail in the field. It's not the best insulation to use on drive systems. And finally, cables are capacitors. And the way that works is the formula is C equals 7.36 epsilon over log D over D. Now, epsilon is the dielectric constant of the insulation, and small d is the diameter of the conductor, and big D is the diameter over the insulation. Well, if you think about it, a thinner insulation is going to have a smaller D over D, and a smaller number on the bottom is going to increase my C. It's going to increase my capacitance. THHN has the highest dielectric constant of any insulation material we use. So that higher dielectric constant, epsilon, that's going to make my C bigger, my capacitance bigger. It also has the thinnest insulation of any cable that we make. So it's the highest capacitance cable we make. And it's not a good cable to be used for drives. Why? Well, without drives, it's not really a problem because 60 hertz is a pretty low frequency. And this cable will have a capacitance, but like I said, it's a low frequency. So I'm going to push most of my current down to that motor, and I'm going to leak very little to ground, and everything's going to work fine. But if I put a drive in here, which has a lot higher frequency components in its power waveform, I'm going to leak a lot more current to ground, and less of it's going to get down to the motor. And that can cause issues. And these are the issues that Rockwell engineer that I was talking to in North Dakota was alluding to when he asked if we made a VFD cable with PVC insulation. We don't, but some other companies do. And his customer was using one such cable, and he was getting drive trips, he was getting drive failures, he was getting all kinds of problems occurring because of this issue. Now, everything else being equal, THHN can have 10 times the capacitance of a drive cable constructed similarly from other, thermoset compounds. So you can only run 1/10 the distance as you could with a true VFD cable. So how can we fix this? Well, one way to fix this is buy a bigger drive, right? Now we just send more current down. We still leak a ton to ground, but we get enough down to the motor to have it work. And if you're dealing with a system where it'd be expensive to replace the cable, and you've got a fractional horsepower drive, this is probably the most economical solution for you to do. But the better solution is size things, spec things up front correctly, so that you use a cable that leaks less current to ground. You don't have to upsize your drive, and everything can work. So in summary, for cable insulation, PVC has issues with a lot of things, right? We talked about all these. They're not good in drive systems. Now, THHN is a great product for building layer applications. It's just a bad cable for variable frequency drive applications due to the high frequencies involved. For VFD systems, Southwire recommends thermoset insulated cables for all drive to motor cables. Now, a PVC jacket is acceptable because that's mechanical protection that's outside the overall shield. Just you don't want to use PVC for the insulation. And the voltage rating should be 600 volts or higher. While that doesn't handle those peaks, I shouldn't say it doesn't rate that cable above the voltage seen by those peaks. I'm not aware of any 600 volt rated thermoset insulated cable ever having an issue. It has a robust enough insulation to not be an issue. Now, there's other solutions out there, right? What about load reactors or DVDT filters? And they can fix some of the issues that VFD cable is designed to mitigate. But if you're looking at EMI or common mode current control, your best bang for your buck is with a VFD cable. Now, sine wave filters exist, and what they can do is they can mitigate the issues in VFD systems where very long lengths are used. Sine wave filters are typically used if you've got a larger, older motor that you want to use and you don't want to have the windings short out on it. Those sine wave filters will literally eliminate that reflected wave, but they're expensive and bulky, and they've got to be matched for proper performance. But they do work. In general, VFD cables do a great job at two things: reducing EMI and controlling common mode currents. They don't do anything to reduce your reflected wave voltage. They don't do anything for harmonics. For those situations, you need other devices. So what we recommend is start with VFD cable. And then if you need some of this other protection, you can add that later on. Most devices are more complementary than competitive. It's really not an either or in these situations. Now there's various cable constructions out there, various different shields. There's three primary shields for VFD cable. One is a continuous corrugated aluminum armor. It's welded, so it's completely impervious to gases as well. It's designed for use in Class 1 Div 1, and this makes a great shield. We also have copper tape shield VFD cables where we helically apply a copper tape over the cabled core. And then we have copper braid constructions with a foil, aluminum foil underneath as well for shield constructions. We don't use interlocked armor on a VFD cable because the interlocked armor is not continuous. Where the interlock happens, you can get corrosion, and that can increase your transfer impedance of that shield. Whereas the three shields above have a much lower transfer impedance with high frequency signals, because we want a really low impedance path back along that cable shield to the drive from the common mode current that was pushed down the conductors of that cable. We also have terminations. We have Armorex cable glands for the welded aluminum armored cable. We have glands that will work for our copper tape and copper braid, and then we have the termination kits as well. If you don't properly terminate these cables, you lose a lot of the advantage of them. So it's very important to consider termination. Now, we provide easy access to our VFD cable information, and the easiest way to get to our spec sheets is go to industrial.southwire.com. Click on the magnifying glass up there next to the Ask an Expert button, type in VFD, and all of the VFD cables and accessories will show up for you. You can click on any one and download a spec sheet. Similarly, for application notes, if you click on the tech blog on the main page there next to products, and you enter VFD, then all the VFD application notes show up. And we've got, I don't know, 5 or 6 of those, I think, as well, which are great reading right before bed at night, I suggest. Now, we have other tools to help you as well. We have the VFD cable calculator. Basically, you enter in this information, and it does all the work for you. It even lists, you can see at the bottom, it lists the sections of the NEC that you have to consider. If you put cable length in, it will calculate your voltage drop as well, and it gives you all the information you need to properly size your VFD cable. In summary, the best VFD cables have an overall shield to reduce EMI, improve your safety and control common mode current, a symmetrical design which reduces the common mode current, allows for tighter bends and minimizes electromagnetic coupling, and a cross-linked insulation which meets NFPA 79-2018, handles reflected waves, and reduces capacitance. Thank you for attending. I hope you learned something and had fun. And if you have any questions, please get with your Reynolds rep, and they can put you in touch with me. Thank you.